14.4 is the flaws of apportionment methods. So remember we have our four methods, Hamilton, Jefferson, Adams, and Webster, but this is going to talk about the flaws. We've got a couple of paradoxical statements here. Alabama paradox, population paradox, and new states paradox. And you're going to have to pay real close attention because it's very specific of when it might happen. Alabama paradox occurs when an increase in the total number of items to be apportioned results in the loss of an item for a group. Population paradox, when group A loses items to group B, even though the population of group A grew at a faster rate than group B. And the new states paradox happens when the addition of a new group changes the apportionments of the other groups. So think about increase in the total number of items, population of group A grew faster, and addition of a new group. That's kind of the three different things that you would need to look at. Belinsky and Young's impossibility theorem. There's no perfect apportionment method. Any apportionment method that does not violate the quota rule must produce paradoxes, and any apportionment method that does not produce paradoxes must violate the quota rule. So it's just saying there's no perfect way to do it. Let's get to an example. Number one, a small country with a population of 10,000 is composed of 3 states. According to the country's constitution, the Congress will have 200 seats divided among the 3 states according to their respective populations. So we don't need to add this up. They already told us this adds up to 10,000. That's useful information. We're going to use Hamilton's method to apportion the 200 seats. So Hamilton's method, we need the standard divisor. Remember, that's the total population divided by the number of items. In this example, that total population is 10,000, and the number of items was the 200 seats. 10,000 divided by 200 is 50. And so that's like 50 people per seat, or 1 seat for 50 people, I guess. So we're trying to apportion this. We're going to use the standard divisor for Hamilton's method and divide by 50. When we do that, 5,015 divided by 50 is about 100.3. 4515 divided by 50 is about 90.3. And 470 divided by 50, you get 9.4. Hamilton's method, we're going to round down. That makes this 100, 90, and 9 for a total of 199 seats. We can see that there should be one more, so we've got one surplus that we have to give out to the highest decimal. And so you're looking at the highest decimal, 0.4 is higher than 0.3. So we're going to give that surplus item over here to group C. And so group C is going to have 10, group A is going to have 100, group B is going to have 90. And that would be Hamilton's apportionment. Now we're going to change something slightly. A change in the country's constitution increased the number of seats to 201. Use Hamilton's method to apportion the 201 seats. So we're doing basically the same thing, only this time it's 10,000 divided by 201. When I do that division, I get about 49.751. I would just round off to a few decimals. Doesn't really matter, I suppose. But then we have to redo Hamilton's apportionment. So those totals, the group populations were 5,015, 4,515, and 470. That came from the table above. Yeah, there we go. But we're going to divide by this standard divisor. So let's divide. Divide each of those numbers, each of those group populations, by the standard divisor of 49.751. And in A's case, 100.80, B, 90.75, C, 9.45. Again, it's Hamilton's method, so we know to round down. That means this is 100, 90, and 9 for a total of 199 again. And again, we have this one surplus, one extra item that we need to give away. And we're going to give it to the one with the biggest decimal. Adding 1, we're going to get 101 for A. B still has 90. C has 9. And so there's our new Hamilton's apportionment. So if you compare this result, there's a paradox that exists. Part C says, if a paradox exists, tell which one and briefly explain why this is paradoxical. So go back to the definitions. This is the one that talks about an increase in the total number of items. So the Alabama paradox, that's what I think it is, occurs when an increase in the total number of items to be apportioned results in the loss of an item for a group. So we need to check and see if that happens. We added an extra item to be apportioned, and yet somebody lost one of their seats. So notice this happens to C. Group C is screaming, hey, wait a minute, this isn't fair. We've got one extra seat to be apportioned, but now somehow, for some reason, we have fewer seats. We have 9 instead of 10. This is that this is that Alabama paradox. An increase in seats from 200 to 201 results in a loss of a seat for seat. Alabama paradox. Number 2, a small country with population 10,000 is composed of 3 states. There are 11 seats in the Congress, divided among the 3 states according to their respective populations. The table below shows Hamilton's apportionment of congressional seats for each state. So a couple of things here. First of all, the table is written sideways instead of sideways, it's written up and down. And so the normal table is sideways from this, but those are the important numbers that we would need if we were doing Hamilton's apportionment. But they already did Hamilton's apportionment, and they found A gets 0, B gets 3, and C gets 8. So the work has already been done here for Hamilton's apportionment, but we're going to change something. The country's population increases by 1,000 people, as shown in the table below. Find the percent increase in the population of each state. Percent increase, you would have talked about in algebra class, or percent change, whether it's increase or decrease. But the percent change, in this case increase, is always going to be change over original. That's how you would find the percent change, the percent increase. So what I'm talking about there is for A, it changes by 20. And you didn't really need to show the work there, but the next one's a little bit harder. 2550 minus 2430. Do that subtraction problem, and that gives me 120. And then that third one, the change, it goes from 7890. Actually, I said that backwards. It goes from 7030 to 7890. But that change is a change of 860. That's the change. So divide that by the original. So 20 is the change divided by the original number 540. 120 is the change divided by the original number 2430. 860 is the change divided by the original number 7030. Change over original. When you do that division, 20 divided by 540 gives me 0.037 or 3.7%. The next division, 120 divided by 2430, is 0.049 or 4.9%. And then the last one, 860 divided by 7030, is 0.122 or 12.2%. Those are the percent changes, percent increase. Part B says, if a paradox exists, tell which one and briefly explain why this is paradoxical. So we're talking about the population increases and the percent change. So let's look back at the definitions again. Population paradox says when group A loses items to group B, even though the population of group A grew at a faster rate. Okay, so you got to think about the percent increase when you're talking about growing at a faster rate. So we can see that group C grows the fastest. It's growing at the fastest rate, followed by group B, and then group A is the slowest, I guess. They're all growing, they're all increasing, but you can tell that C is fastest, next is B, and then is A. So if a paradox exists, tell which one and briefly explain why this is paradoxical. Well, we're going to have to find Hamilton's apportionment. But remember, we changed the numbers, right? The one that they did for us was with 10,000, but now we're increasing to 11,000. So we've got to start over, but we've got to use those numbers with the 11,000. All right, so let me just copy the table so I can scroll up. We need to do Hamilton's apportionment and see what happens there. Hamilton's apportionment. We're passing out 11 seats, so let's calculate the standard divisor. The total population is 11,000 divided by the number of items, 11. That's 1,000. 1,000 people per seat, or one seat per 1,000 people, I suppose. Let's divide. We're going to divide by that standard divisor. And we get 0.56, 2.55, 7.89. Hamiltons, we're doing Hamiltons again, so we round down. That's 0, that's 2, that's 7. That only adds up to 9. Looks like we should have 2 surplus items. Give them out one at a time to the highest decimal point. So this one gets 1 for being the highest, 0.89. 8. And then next is 0.56. 1. So Hamilton's apportionment says A gets 1, B gets 2, C gets 8. But that's not the question. The question says, if a paradox exists, tell which one. Is that a paradox? Is there a paradox here? A gets 1, B gets 2, and C gets 8. Originally, remember, before the change, it was 0, 3, and 8. Okay, so what does that mean? A now has 1 instead of 0. B has 2 instead of 3. If you notice, B lost 1. B had 3, now they have 2. B lost 1, but A gained 1. But what you're supposed to do is you're supposed to notice that B's population is growing faster than A's population. Well, that's that population paradox. Population paradox. Go back and look at the definition if you need to. Population paradox says when Group A loses items to Group B, even though the population of Group A grew at a faster rate than Group B. This is exactly what it says. B's population grew faster than A's, but B lost a seat to A. That is the population paradox. Number 3, school district has 2 high schools, East and West. East has enrollment of 1688, West has enrollment of 7912. The school district has a counseling staff of 48 counselors who are apportioned to the schools using Hamilton's method. This apportionment results in 8 counselors assigned to East and 40 counselors assigned to West. So they've already done all the math, they've already done Hamilton's method, and we see East gets 8 and West gets 40. Part A says find the standard divisor, then tell what this means in the context of the problem. So remember, standard divisor is the total population divided by the number of items. Total population here, I guess, is this 9,600. And we are apportioning, how many was it, 48? 48 counselors. When you do that division, that's 200. And the standard divisor is 200. Then tell what this number means. Well, look at the units. 9,600 was people, and 48 was counselors. So it's 200 people per counselor. Or, in other words, 1 counselor per 200 people. Sometimes I think it's easier to understand when you look at it that way. But this is the standard divisor, 200. 200 people per counselor. Part B, suppose a new high school, North High, with population 1448 is added to the district. Using your result from Part A, how many counselors should North High have? Okay, well, North High has 1448, and we know there's supposed to be 200 people per counselor. So just a kind of a quick, simple estimation, it tells me that this should be about 7. There should be about 7 counselors. And I don't want to get any more accurate than that. Obviously, there'd be a decimal, but we can see that it's about 7. 1,400 divided by 200 is about 7. So 7 counselors for North High. Part C says the district hires 7 new counselors. What a coincidence. Use Hamilton's method to reapportion the counselors. So now we have 7 more. There were 48, now there's 7 more. So now we've got a total of 55 counselors. We've got to apportion those 55 counselors. Now I didn't give a whole lot of room here, so make sure you write small. East High had 1688. West High had 7912. And North is the new one, North High 1448. If you add those three numbers up, that gives us a total of 11,048. 11,048. All right, so if we're going to do Hamiltons, that's east, that's west, that's north. If we're going to do Hamiltons, we need to find that standard divisor. Standard divisor is the total population divided by the number of items. When I do that division, that gives us about 200.87. Standard divisor is 200.87, or 200.87 people per counselor. We're going to divide by that. This is Hamilton's method, after all. Doing that division gets me 8.40, 39.39, 7.21. And we're doing Hamilton's method again, so again we're rounding down. Keep in mind, if it was a different method, maybe we'd round up or round nearest, but Hamilton's always rounds down. Round down to 8, 39, and 7. 8 plus 39 plus 7 is only 54. So we can see there's one surplus item that we have to give out, and we're going to give it to the highest decimal point, 0.40. So add that on, and east gets 9, west 39, north 7. That would be this Hamilton's apportionment. Part D says, if there's a paradox, tell which one and briefly explain why this is paradoxical. Well, if you read the definitions, it should be obvious that this is going to be new states. But like, really go back and read that definition. The addition of a new group, well, yeah, that's what we did, changes the apportionments of the other group. So this is kind of what you have to make sure that happens. Did adding a new group change the apportionments of the other groups? I bet it did. So check it out. At the beginning of the problem, East got 8 and West got 40, but now East gets 9 and West gets 39. So that's kind of weird. We added 7 new counselors for this new high school. Why should that change the apportionment of the other schools that were already there? The addition of a new school caused the apportionment of East and West to be changed from 840 to 939. Last slide is kind of a summary and what could happen, when it will happen. Check it out.